All right, welcome to the UC Davis Tahoe Environmental Research Center State of the Lake presentation with our director, Dr. Jeffrey Schlado. We will have the chat on if you have any questions for me, but we will not be moderating the chat for the question and answer session. So if you would like to add questions, you can add them using the Q&A button at the bottom. You'll see the two little bubbles and it says Q&A. And you are automatically muted and your video is off. You don't have to worry about that. You can eat your lunch while Dr. Schlado presents. And I'm going to turn my video off and mute myself as well. It is not currently being shared on Facebook Live, but we are recording this and we'll be posting this on our YouTube channel. And I'll post that link in the chat for anyone who is missing this. It will also be available on our on the website. So without further ado, I'm going to turn it over to Dr. Jeffrey Schlado.
Thank you, Heather, and good afternoon, everybody, and thank you for being here. I had hoped several weeks ago that our days of virtual presentations were behind us, but once again, my predictions proved to be overly optimistic. So here we are, the Tahoe State of the Lake Report 2021. Before I start, I did want to acknowledge the organizations, companies, agencies that are kind enough every year to help defray the costs of producing this report. Some of these agencies are also the agencies that fund our monitoring and our research. So I wanted to acknowledge that as well, because without that support, there would be no data, short-term or long-term, with which to make any kind of assessment. And also, by way of prelude, I wanted to acknowledge our staff, our students, our faculty, everybody at TERC. This last year, as you all know, has been tremendously trying for everybody in so many ways. Aside from a 6-week period when there were mandatory stay-at-home orders in place, we kept up the work as best we could. And that often meant taking extraordinary measures beyond masking. I mean, when you're trying to do a 2 or 3 person job, but you can't be in close contact, it makes it really difficult. In the absence of knowledge to the contrary, early last year, everything was being disinfected, boat handles, because everybody was concerned about helping towards the spread of COVID. So again, to all of you, thank you. Thank you for those extraordinary efforts, but they aren't over yet. Okay, so the most frequently asked question of 2020 and 2021, it turns out, is has COVID-19 affected the health of Lake Tahoe? Good question. Actually, the map here is something from last week. This is the level of community transmission in every county in the country. And as you can see from the red color, COVID-19 is being transmitted at an incredibly high incredibly high rate still to this day. So this is not behind us. But to answer that question, has it affected the health of Lake Tahoe? That answer was no. Or at least to the best of our knowledge. Certainly, there seems to be no impact that we can resolve on clarity, on biological health, on all the usual measures of lake health. One of the things we don't know about is what the impact was of all those extra people in the Tahoe Basin. So we've just concluded our first year of monitoring microplastics in the lake from top to bottom, in organisms, in drinking water. And once those data are analyzed, we'll know what it was in 2020 and early 2021, but that will just be our benchmark. We won't know what it was in the years before COVID. So we'll see. But again, to the best of our knowledge, COVID-19 did not affect the lake. Okay, so let's just zip through some of the highlights, let's call them that, of 2020. So even though this is the 2021 State of the Lake Report, we are primarily presenting data from the year 2020. So many of these graphs in this first part are going to take the form shown here. It's a time series plot. So in this case, the data goes from 1910 up to 2020. What we're showing here are the air temperatures. The bottom panel, the blue, are the minimum temperatures. The upper panel are the maximum temperatures. And 2020 is obviously the last bar on this graph. So it was a warm year. You can see both the minimum and the maximum temperatures exceeded the long-term mean. The important thing to take away from this is how temperature is increasing. And if you just look at that bottom plot, the minimum temperatures, you can see since 1980, in the last 40 years, there've probably only been 2 or 3 years where the minimum temperatures have been below the long-term mean. 2020 was also a dry year. So this is precipitation measured at Tahoe City. The dashed blue line is the long-term mean of precipitation. And here we are in 2020, and we're well below that mean. Something like the mean is something like 31 or 32 inches. As a consequence of that dry year, the lake level fell. So this is the squiggly blue line here is the lake level. This is measured by the U.S. Geological Survey at a station at Lake Forest on the North Shore. Here at the end, I guess 2020 and a bit of 2021, we can see the lake level falling. So during calendar year 2020, it fell almost 2.5 feet. And when you read about Shasta Dam and other reservoirs falling 60 and 70 feet this year, that seems insignificant. But for Tahoe, it's incredibly significant. These dashed lines, this represents the top of the dam at Lake Tahoe, 6229. Lower line is the natural rim, 6223. We have 6.1 feet to play with between when the lake stops flowing and when it overflows the dam. And so lake level fell 2.4 feet out of that 6.1 feet of freedom, let's call it, that we have. The surface of the lake, the water temperature, also got warm. So again, these are just the annual average surface water temperatures. You look on the left axis, there's the temperature in Fahrenheit that many of you may be more familiar with. It seems very cool. Remember, this is the average over the year. So our winter water temperatures are cold. The important thing is this is the trend line since 1968, and we're above it. All right. July and August are the warmest months at Tahoe. And so what we do here is compile the average July temperature. So these are from data that are taken every 2 minutes, 3 foot below the surface of the lake. And you can see that July 2020 was pretty average, maybe a little bit below average. Of course, we can barely remember 2020, but we do remember last month. So July 2021 was a record warm year. It was 68.7 degrees Fahrenheit. And the average in the middle of the lake, 3 foot below the surface. And the warmest temperature was 72.5 degrees during that month, which was also a record. Now, I imagine some of you are saying, what's the big deal? It's nicer to swim when it's 72 degrees than when it's 68 degrees or 65 degrees. Well, the big deal here is that we're approaching a threshold, a threshold where Lake Tahoe hasn't been before. So this temperature of 20 degrees Celsius, 68 degrees Fahrenheit, is actually a threshold for cyanobacteria. So cyanobacteria are, if you like, a different form of algae that can exist. Typically, they don't exist when temperatures are below this threshold, 68 degrees Fahrenheit. Because you're warmer than that doesn't mean you'll necessarily get them, but it is a necessary condition, it seems, around the world for cyanobacteria. If you're not sure what cyanobacteria in a lake would look like, here's a photo taken 2 days ago from a lake that does suffer from cyanobacterial blooms. And it's A, it's not pretty, and B, they can be toxic. All right, moving on. Another consequence of the warming temperatures is what we call the stratified season is lengthening. So what does stratified season mean? The surface of the lake is warm, the bottom of the lake is still very cold. That difference in temperature translates into a difference in density. So we basically have light, warm water floating on top of cold, dense water. And that inhibits the mixing of the lake. So the longer that condition persists, the less mixing of the lake there will be in the winter when mixing typically occurs. It always occurs. What changes is how long it mixes for. And that's what this plot shows. This is sort of an inverse plot. So the top of the plot here on the left is the surface of the lake. Down here is the bottom of the lake. And these bars indicate for every year, typically in March, how deep the lake mixed. So here we are in 2020. It literally only mixed about 450 feet. Actually, because we've already had March in 2021, I added that value too, which was essentially the same. So the lake did not mix very deeply in these last 2 years. So again, so what? You live at the surface of the lake, not at the bottom of the lake. Why should you care about what happens at the bottom of the lake? Well, it's incredibly important because a lot of chemistry happens at the bottom of the lake. Actually, right now, very little chemistry happens at the bottom of Lake Tahoe because there's so much oxygen there. But if oxygen was to be reduced, suddenly the chemistry gets very interesting, very exciting. Things like nutrient release from the bottom of the lake takes place. So how do we know that we're not getting as much mixing at the bottom of the lake as we used to? This is, I guess, a very strange way to look at it, but very effective. What I've plotted here is the temperature at the bottom of the lake. So this blue squiggly line represents the measured temperature at the bottom of Lake Tahoe. These dashed vertical lines represent those years when the lake mixed all the way to the bottom. So one of the things that happens when the lake mixes all the way to the bottom is that the temperature drops. So if we look here around the year 2000, the bottom of the lake was slowly getting incrementally warmer, and then we had deep mixing, it cooled down, and then a second year of deep mixing, it cooled down a lot. And then with the absence of mixing, it starts warming again. What's notable here, and I don't want to use the word ominous, but let's call it noticeable, is that over the long term, the bottom of the lake is getting warmer, which is changing metabolic rates and indicative of the lake departing from the conditions we're used to. The most recent deep mixing event 2 years or 3 years ago caused this cooling, but now we're back up on this warming trend. Okay, streams, we're all familiar with Lake Tahoe streams. They bring in lots of stuff. They bring in sediment, they bring in nutrients, and here is just an example of one of the streams. This is the Upper Truckee River, the largest stream. And this is a measure of the load of nitrogen brought in by the stream. Each year, the dark blue is say total nitrogen, the light blue is nitrate, which acts as a nutrient for the lake. And over the long term, it stayed pretty flat. This is 2017, that was that record rainfall year that we had, rainfall and runoff year. So it was a huge load of nitrogen brought in, but it has diminished back to relatively low levels. Within the lake itself, however, nitrogen has not decreased or stayed flat. It's rising, as is phosphorus, the other key nutrient. And why this is happening is, well, it could be for a number of reasons. Streams aren't the only source of nitrogen and phosphorus. Urban runoff is another source. The atmosphere is yet another source. And the way nutrients are processed within the lake is also changing. This is a very simple graph, but it's actually, there's a lot of complexity that contributes to it. And a lot of that complexity is still trying to be unraveled. Another metric of the health of the lake or the condition of the lake is the chlorophyll or the algae in the lake. And overall algal biomass, again, looking since, in this case, since 1984, has stayed relatively constant. It's not dramatically going up or going down. What is changing are the cell sizes. So these are free-floating algae, little cells that carried by the currents. And while the total amount of biomass is the same, the average cell size is decreasing. And this is important from the point of view of clarity because it's only the small cells, the very tiny cells, the cells that are a couple of microns in diameter that affect light. Okay, so that's it as far as a snapshot of some of the results in the State of the Lake report. So one could think at this point, we could say, what is the state of the lake? Are we a happy face? Are we concerned? Are we sad? Where are we? Well, trying to give a numeric or iconic value to the state of the lake is not what the report is about. It's not what we try to do, mainly because it has no meaning. There's so much interannual variability. There are extreme events. Looking at one value 1 year really teaches us little and either gives us false confidence or the opposite if we were to try to do that. So instead, to at least give you some sense of the state of the lake, I want to focus on 3 examples with a little more detail. So those 3 are going to be looking at the clarity of the lake, looking at nearshore health, and looking at climate change. And to sort of end it all with a potential solution that bears on all 3 examples. So, I mean, we all know talking about climate change is rarely a feel-good topic. So I don't want to end with on a downer. So the solutions are really what we should be feeling good about. Okay, so clarity. So I guess we all know, hopefully, that one of the key metrics at Lake Tahoe for its health is its annual clarity. And each of those blue dots represents the average of about 25 points taken throughout the year. The photo on the left shows our field director, Brant Allen, doing what he does many weeks of the year, looking down at the Secchi disk, and he's then going to lower it, and the depth at which it disappears, he records as being the Secchi depth, and that becomes one of those 25 points each year. So you possibly familiar with the story. So from 1968 till about 2000, there was a pretty steady decline in this value, the annual clarity. For about the last 20 years, it's flattened. There is no statistic. If you just look at the data since the year 2000, there is no statistical improvement or decrease in the annual clarity, and that's great. It's a great achievement to say that clarity, the decline in clarity, has been stopped. But this is where we want it to be. At least by 2025, agencies in the Tahoe Basin had set a clarity challenge to achieve and sustain clarity nearing 80 feet by 2025. So we're not there. And it doesn't mean just having one point hit 80 feet or come close to 80 feet. It means, as it says, sustained clarity nearing 80 feet. I should remind you all that this is the target. The actual target is 100 feet. So there's been some progress, but it's not where people wanted it to be. If we look at the winter, so this is just now taking the months from November through March. This is how I define winter. You can see there that here there has been improvement. There has been an increase in Secchi depth. If you look over the last 10 or 20 years, yeah, maybe there is a sustained value of 80 feet that has been attained. So maybe that clarity challenge has been met for the winter. Summer, on the other hand, is a different story. Summer, that linear trend has stayed pretty much unbroken since we started taking 25 measurements a year in 1968. And certainly climate change is one key driver to this trend. Okay, so that was sort of example number one. Example number two relates to metaphyton. And metaphyton is something many of you may not be familiar with. It relates to phytoplankton, to algae, but these aren't the free-floating algae that are in the lake and being moved by currents. These aren't the algae that cling to rocks and make those rocks slippery and slimy around the shoreline. These are algae that are more filamentous, long and stringy and sort of clumped together and just sit on the bottom of the lake and may be moved as en masse by currents and waves. So on the left here is, I guess, a beautiful, beautiful photo at the bottom of Lake Tahoe. You see the little sand waves, the ripples, and you see the sand, and it's clean. This is what parts of Lake Tahoe's bottom look like now. So what we're seeing here is shells, Asian clam shells. The animal itself has died, but this is the shell that's left behind. Its relatives, future generations, are living just below the surface, burrowed down into the sand. That big green clump you see, that's metaphyton. And all those smaller little patches of green you see are smaller fragments of metaphyton. So this is what the near shore looks like along much of the south shore and the southeast corner of the lake, and a few other places around the lake as well. So this was first noticed in about 2008 in Marla Bay in the southeast. It's still there in Marla Bay, possibly not as extreme as it was in 2008, but say 2019, looking down into the water, you could still see these patches of metaphyton. Reagan Beach on the California side what we're looking at here are metaphyton that have been washed up. So they're not growing on the beach, but they've been washed up. This 2014 was a very low water year, so that seems to be the time when it gets washed up more frequently. It decomposes, it smells, it's not an attractive beach. So that's not a good look for Lake Tahoe. And again, in 2019, they were present in large numbers. The brownness of the water there isn't sediment coming in from the Upper Truckee River. This is just the metaphyton that's been, I guess, separated by the waves breaking on the shore. All right, to give you a sense of what this may look like if you were scuba diving. So what we're seeing here are just small bits of metaphyton on a relatively clean sandy bottom of the lake. But what the diver is swimming towards is a patch of clams. And so you're starting to see the clam shells, you're starting to see the larger patches of metaphyton. As I said, this isn't just one place where it happens to be bad. This is a very common sight throughout much of the South Shore. Okay, got to move this thing out of the way. All right. So why the association with Asian clams? Asian clams are filter feeders. They're very efficient at filtering the low levels of phytoplankton in Lake Tahoe to get their own food. They filter them, they concentrate them, they use them to grow, and then they excrete them. And the excretions contain levels of nutrients 10 or 20 times higher than what you would find in the lake. So effectively what they're doing is they're creating an environment, a high nutrient environment, and they're the conditions the metaphyton like. The metaphyton are not an introduced species. They're all along, but they were never in nuisance. They were never present in large numbers because the concentrations of nutrients were not large enough to support them before Asian clams came in. So the metaphyton density and aerial spread is going to increase. It's something we're pretty sure about with climate change. In part because of the warmer waters will allow the Asian clams to metabolize faster, grow larger. We have data to show that the larger they grow, the greater their excretion, their filtering rates and their excretion rates. You can look outside your windows. If you're in the Tahoe Basin now, it's smoky. When it's smoky, the amount of UV radiation from the sun is dramatically decreased. UV radiation, it turns out, is really an important, let's call it a disinfectant. And when Asian clams reproduce, they send out these little larval beings. Let's call them babies. It's not the technical term, but let's call them Asian clam babies that are highly sensitive to UV radiation. And a relatively short exposure can kill them. With reduced UV, that doesn't happen. The potential for them to spread is dramatically increased. As I said, with low lake levels, the metaphyton seem to be washed ashore far more frequently. So what can be done about this? Well, I think where initially, and this is the work we've been involved in the last few years, I guess initially starting with support from the Nevada Division of State Lands, is developing methods to map the distribution. Where is the metaphyton? Using drones and helicopters and scuba divers taking on the ground, under the water measurements. Also using models, so starting to use models to understand what the distribution of it is. They move around. These patches may start off over the Asian clams initially, but then currents and waves move them. So in a way, that's work that's already underway, and the picture shows just some of the cameras attached to helicopters and drones as we try to at least put bounds on the size of the problem. Another thing that could be done could be clam removal. Clams are the root cause here. But clam removal is difficult. We've developed methods for doing it, but this is very person, diver intensive, and it costs money, and you never remove them all, and within a few years, they're back. So it's an ongoing issue, particularly when there is no market for clams or clam shells. Another option that we're playing around with now is, well, let's harvest the metaphyton. In a way, the clams are doing us a favor. They're concentrating nutrients. The metaphyton are taking up the nutrients. Maybe if we harvested the metaphyton, we'd be removing nutrients from Lake Tahoe. That's sort of an idea that's sort of still being scoped out. Maybe it has legs, or maybe it's just too expensive to be meaningful. And another option is, well, we could just ignore it. I would argue that's not a good thing to do. It's what's probably been happening to a degree up till now. As I said, it's only going to get worse, and the solutions are only going to get more difficult and more expensive the longer we wait. Okay, so I should have given a spoiler alert for this. Okay, Tahoe Tessie isn't real. Neither is the Easter Bunny. But climate change is. And so the third example I'm giving now is climate change. So some of you maybe have noticed or heard that at the beginning of this week, the IPCC, the Intergovernmental Panel on Climate Change, released a report, Climate Change 2021, the Physical Science Basis. So this is actually the first of 3 reports. So this one deals with, as it says, the physical science and the modeling and the understanding of what's contributing to climate change. Next year, there'll be a second report. I think that one deals with adaptation and policy, and then there'll be a third report dealing with other aspects of this. So this report is 3,949 pages long, and when I downloaded it on Monday, I set about reading it. Okay, I got to page 18. And that was pretty dense up to that point. But I stopped there, among other reasons, because this is what I read. And I quote, global surface temperature will continue to increase until at least the mid-century, and part I've underlined here is under all emissions scenarios considered. I'll come back to that in just a second. So global warming of 1.5 to 2 degrees C, let's just say 3 to 4 degrees Fahrenheit will be exceeded during the 21st century unless deep reductions in CO2 and other greenhouse gas emissions occur in the coming decades. What they also said, and that may be on page 19 or 20, I'll find out when I continue reading, is that even if our fairy godmother, who also doesn't exist, came along with her magic wand and stopped our carbon emissions now, this minute, we're still going to have those kinds of warming rates continue. And they will eventually abate, depending on what we do, under which emission scenarios we choose to live. But climate change is happening, and temperature warming is just one, temperature increase is just one manifestation of it. The reason I introduced this, actually let me back up a bit and say, so what this report deals with, it's the physical basis, is primarily the modeling that is done, the physical models that are created by a global consortium of scientists backed by just about every country on the planet. And what they more or less have is about 30 models. These are all incredibly sophisticated models that predict not just the warming, the physics of warming of the atmosphere, but the impact that atmospheric chemistry and ground processes and the like have on that rate of warming. And they also reach consensus on what are the scenarios for greenhouse gas emissions into the atmosphere. I mean, they're not going to be the same as they are today. They will be higher if we do very little. They'll be less if we're all good global citizens. But the whole report is dealing with these models and what the future emissions will be like. And this is just the latest of a series of such sort of modeling revisions that have been going on for about 30 years now. So we've been working with support from the California Tahoe Conservancy to use what was the previous set of climate change models and scenarios and to apply them more locally here in the Tahoe Basin. So taking these projected global meteorological conditions for the next 80 years, downscaling them for the Tahoe Basin, and then using them as drivers for watershed models and lake models and things like that. And I guess I want to make the point that just because this new set of models and advances in the physics came out doesn't negate anything in the last round of model results. In fact, it reinforces them. It certainly provides more detail, makes some adjustments, but as you'll see, these things haven't changed a whole lot. So what I'm going to show you now are just a couple of results from these models, from these model runs produced by this team. Slightly different form of plot here. Again, time is on the horizontal axis. So going from 1954, that's when they consider the historical record to be robust enough to use, actually goes up to 2100. What's being shown here is air temperature in degrees Fahrenheit on the left. The gray, actually, let me explain this a little more. So this gray part here represents historical conditions. So this is a model result, but it's a model based on historical data. So the modeling's done, and they do this so they can prove to themselves, confirm to themselves that their model does produce a realistic result. So we used 4 models. These are 4 of these 30 models that have been accepted by both the state of California and the state of Nevada as reasonably representing conditions here being, let's say, the Western US. So this black line in all these plots represents the mean of those four models. It doesn't mean it's the right answer, it just means it's the mean. What this shaded area represents in just about all cases is the upper bound represents the highest most value by an individual model. The lower bound represents the lower value by an individual model. So basically, if you were to plot all the model results here, you'd have this tangled mess of spaghetti and wiring going through here. So this is just a cleaner way to show it. Jumping up to the top here, RCP 8.5. So we had talked before about emission scenarios, how much greenhouse gas is being put into the atmosphere. Well, RCP 8.5 represents one of those emission scenarios that has been agreed to by the IPCC, the Intergovernmental Panel on Climate Change. It represents what was considered to be a pretty high rate of emissions. Turns out our current rate of emissions actually exceed this rate. RCP 4.5 is a lower rate. Now, just so we don't get too comfortable with these terms, in this new report, they've changed the names of these emission scenarios. So this may be the last time you will ever see RCP written. Stands for Representative Concentration Pathway, a term that everybody intuitively understands what that means. It's been replaced by SSP, the Shared Socioeconomic Pathway, a term that's equally transparent and clear. Okay, but looking at the data, what we're seeing is under this warmer scenario, the RCP 8.5, temperatures are increasing. So by mid-century, I'm not going to live to 2094, so I'm not interested. But maybe I'll live to 2050, certainly planning on it. By that time, if I just project across here, air temperatures, they're saying here will be something like 51 degrees. Currently, it's sort of in the range of 47. That's 4 degrees Fahrenheit in my lifetime, not neglecting what's already happened. So yeah, maybe that's not a prediction. It's just saying that's sort of the mean of this higher emission models. It could be higher, it could be lower. Any of them are currently plausible based on existing knowledge. Okay, can't present everything in the report, but I'm going to present just a couple of things. One is the percentage of snow. We know from measurements taken here and elsewhere that our total amount of precipitation is going to stay not that different from what it's been in the past, or so we believe, but the fraction of snow in it is going to decrease. And so this dark line here is the average of the models over time. So under this higher emission scenario, going down to something like 20% by the end of the century. But some models say at that time it could be higher. Some of them say it could be significantly lower. It's likely, if this emission scenario is correct, to be something in this range, which is very different than the climate we've been living in. So I want to dwell now on something that hasn't been talked about here. So as well as the climate models, which really were the driver of this, and the data they give us on future weather conditions, we take that data, we run it through watershed models, hydrology models, and make estimates based on what's given from the future climate on what stream flows may be. So here I've just given one example. This is for Ward Creek on the west shore. Again, this black line is just separating the historic. So this is sort of grounded in what's being measured. And off to the right, it's not grounded, but it's based on the physics as best we understand it of the watershed. And what we're seeing here, I guess the red line is sort of the maximum values predicted by any of our four scenarios, our four models. The blue one is the minimum. So I didn't draw the mean line in here, but it would obviously lie in between the two. The point, and there is a point, historically, 1,000 cubic feet per second has been the maximum daily flow rate observed in Ward Creek. This is the future. And here I am in the twilight of my life. And suddenly we're getting flow rates there of 2,500 CFS. Now, you all obviously realize that it isn't just Ward Creek that's running this high in this year potentially, but it's every other creek at the same time. This higher rainfall we're having we've lost the snowpack, or at least large parts of it. We don't have any storage, so the precipitation is rain. It's transferred to the stream very quickly. Maybe there is some snow, and so we're getting rain on snow. So we're getting this large inflow. If we think of all 63 streams around Lake Tahoe flowing at record high levels, possibly 2 or 3 times what they've flowed at in the past, it's going to have an impact on the lake level. And that's what is being shown here. So again, this is showing for this RCP 8.5, the maximum water surface change in a day. Now I have the axis, the vertical axis is in water surface change in millimeters. So 250 millimeters represents 10 inches, or it is 10 inches. So what this is saying is, under these conditions, when Ward Creek and all the other creeks are flowing at these unprecedented levels, and of course we're getting precipitation on the lake itself, the water level will rise 10 inches a day. Remember, we have 73 inches between the natural rim and the top of the dam, and it's rising at 10 inches a day. It doesn't necessarily mean that it started when we were at the natural rim. This could be happening when we're already a foot below the dam. So this has some very serious implications about what happens to streams at Tahoe, what happens to the shoreline at Tahoe, but probably most important for the people downstream of Lake Tahoe. So some key results from the report. We're going to have a warmer lake. This is going to favor invasive species. We'll have faster metaphyton growth because of that. There'll be much higher and earlier peak stream flows. This will exacerbate flood risks and risks to infrastructure. There's going to be longer and more intense droughts, serious consequences for forest health, for wildfire. I mean, it's everything we're experiencing now, and it's going to be more of it, more intense. The lake is going to be more stagnant. It's going to mix for less time and less frequently, with the result of potentially having hypoxia, meaning lowered oxygen levels at the bottom of the lake. And the lake level itself is going to depend on management of releases from the dam at Tahoe City. That's something that couldn't be modeled, how that's going to be managed in the future. But there's going to be a greater need for forecasting future weather conditions in a way. The dam at Tahoe City has a very limited release rate, nothing like 10 inches a day. So there's no possibility that something like that, or 6 inches a day, could be counted by dam operations. This presents a real challenge to people, both sides of the dam. I don't want to create the impression that agencies and people in the Tahoe Basin haven't been thinking about this. They have, and there are climate adaptation plans. The point of this is now that we have finally some more specific numbers on what the consequences are, and also that I think with this IPCC report, the urgency is being heightened to not just create plans and action plans, but to actually rapidly start thinking about them. Okay, so I said I would end with a solution, and the solution really is tied to ecosystem recovery, because ecosystem recovery and the health of the lake is the real goal. Clarity is an incredibly important concept. It's not a concept, it's real. It's an important metric. It tells us a lot about the health of the lake. It doesn't always tell us why it's up or down. But we're trying to move beyond just having improved clarity, but having an improved ecosystem. And so the solution that I think there's a lot of potential and deserves consideration and action. Well, before I do that, just making this point that multiple approaches are essential. I mean, till now, most of the focus has been on watershed processes, and they have, as I've showed earlier, they're having results, particularly with winter, the improvements in winter clarity. But we really need multiple approaches, and especially those approaches that bring no regrets, meaning that if they don't work, we haven't shot ourselves in the foot by building something that can't be unbuilt, like building a dam across Emerald Bay, a bridge across Emerald Bay. Okay, so this is Lake Tahoe in 1960. This is a sort of simple picture of the food web. So the top predator at that time was the Mackinaw. It had supplanted the Lahontan cutthroat trout, which we had overfished decades earlier. They fed on little fish, on minnows and the like. There are also kokanee, rainbows. Both of these, well, actually, the Mackinaw fed on these smaller fish, but the smaller fish largely fed on Daphnia. So Daphnia is this tiny little zooplankton that's an indicator of high water quality around the world. And the reason for that is that they're very good at filtering out sediments and fine algae from lakes. So they consume them. You could say, how can they eat dirt? Well, they don't enjoy it. They just do it because they shovel things in their mouth, but then they excrete them as larger fecal pellets that drop to the bottom of the lake. And so they've effectively removed fine sediment, tiny algal cells. And this was what all of which contributed to Lake Tahoe's astounding clarity of 100 feet back in 1960. Okay. 1964, the mysis shrimp was introduced to Lake Tahoe and Emerald Bay and many other lakes in the region. What it did was decimate the Daphnia population. Daphnia are delicious, as we all know. They're also the perfect size for mysis to eat. So suddenly we've got this rupture in the food web. The minnows, the kokanee, the rainbows have lost a really nutritious food source. The Mackinaw can still eat them can still eat them, but their numbers and their sizes are diminishing. Without the Daphnia present, algal cells proliferate, fine sediment proliferates, there's nothing there to remove it, it sinks very slowly, and the clarity of the lake diminishes. All right. And these arrows just show those trends that I just mentioned. If you haven't seen mysis before, this is what they look like in a jar. They're about the length of say the width of your little fingernail. They look kind of cute there, but if you look at them up close, they're really ugly, I think. But who am I to say? Okay. The evidence of what I'm proposing here and have been proposing for a couple of years now results to observations made for 6 years in Emerald Bay. So Emerald Bay, which also had mysis, in beginning of 2012, the mysis disappeared from Emerald Bay. The reason is probably because of a reproductive failure. They only live 1 year, and if you have a reproductive failure in 1 year, then there aren't very many of you to tell about it the following year. So their numbers were down here around 0. This dashed line is their usual numbers of around 100 in Emerald Bay. Daphnia, what had been sort of largely driven out, eaten by mysis, again at the beginning of this period was down here near 0, but in the absence of mysis, it rebounded. It rebounded to 3,000 and 4,000 of them in a cubic meters of water, very close to what it had been in its heyday in Lake Tahoe. When this happened, this is clarity. Clarity went from about 40 feet to 70 feet in something like 2 years. Okay, reproduction is a fact of life. The mysis eventually got their mojo back, whatever. They started reproducing again, and then they've been sort of oscillating around their historical value ever since. Once the mysis were back, the Daphnia decreased. Once the Daphnia were gone, the clarity decreased. You could say pure coincidence. I would say otherwise. Okay, so I know I've been very critical of the looks of mysis and other things like that, but they aren't all bad. It turns out, because they have the good fortune of living at Tahoe, mysis are incredibly healthful. They're very high in protein. They're very high in lipids. And lipids are, if you take things like salmon oil for omega-3s, they're the lipids. And so mysis have almost a third of their lipids are omega-3s, which are the best of these fatty acids. If you compare that with salmon, it's double what we get from salmon. So suddenly, this is something that doesn't belong. Obviously, to remove something out of a system takes money. What this is saying is, maybe there's some money embedded in this creature. And if only there was a way to turn this into a useful product, then maybe the cost of removing it could be offset. And that's exactly the process that UC Davis Graduate School of Management went through, at least that thought process, looking at how mysis could be used. One of the, I guess, a solution that they found that seemed to bear out both financially and as being practical in a short term was to harvest them and then regenerate them into a useful product. And it could have been those same pills we take to increase our own omega-3s, but there seem to be fewer regulatory hurdles and a quicker path to turn them into very high, delicious dog treats as a way of suddenly engaging people's awareness of invasive species, ecosystem health, a whole range of products, potentially based on some of the assumptions in the financial model. This could actually generate funds rather than taking funds exclusively. That it could be possibly cost neutral, or there could be funds to support further research on the Lake Tahoe ecosystem. So the advantages of this is it could help meet the clarity challenge quickly. Early on, we showed the clarity challenge still seems to be a challenge. It does this by restoring the system so that particles and fine algae that reduce clarity are removed internally to the lake. We're not just relying on watershed projects to do that. If a lake is clearer, because the removal of these fine particles, it's a cooler lake. So that threshold of the lake's getting warm, nicer for swimming, but poorer for invasive species and possibly even cyanobacteria, we're starting to steer away from that threshold. Clearer lake gives us greater UV penetration. It wards off invasive species, including Asian clams. As I said, higher UV levels means their ability to successfully reproduce is thwarted. And the same with goldfish, and the same with all the other warm water fish that have been introduced to the lake. You get rid of mysis, you bring back Daphnia, suddenly you're bringing back the ecosystem that the native fish, the minnows, and the like used to have and grew plentiful on, and the game fish, like too, the kokanee, the rainbow trout. Talk to fishermen, and they'll all say there aren't as many and they're way smaller. And the no regrets part. Hey, We do this, and if after a year or 3 years or 5 years, there are some unforeseen bad results, you stop, and I guarantee mysis will reproduce enough to get back to where they were. So there's almost nothing to be lost. And finally, another advantage is this is a new local industry. We're not just talking about Emerald Bay, we're talking about Tahoe, and this would be an ongoing industry. Okay, the disadvantages, I haven't found any yet, but you might say I'm biased. Okay, that's it. Thank you for attending, listening, humoring me. And I guess, Heather, we're going to try to answer some of the questions, especially the easy ones. Remember, no hard questions.
Perfect. I'm going to give you the easiest softball to start out with. So it is 1 o'clock, but hopefully we can stay on for another 10 minutes. We've got about 19 questions. Here's the easiest question for you. Why don't the fish eat the mysis?
Wow, why don't the fish eat the mysis? Mysis, although not the most attractive organisms, are some of the smartest. What they do is during the day, they migrate vertically to the bottom of the lake, go down maybe 1,000 feet. It's dark there. Most of the fish are side feeders. They can't see them. At night, they come up to the surface. Again, it's dark. Fish are side feeders. They can't see them. So they largely minimize predation. But then they, with those big eyes they have, they can see the zooplankton and they can keep chowing down. So yes, they're smaller than us, but they seems like they're smarter than us too.
Great. Another easy one for you. How will harvesting the mysis impact the fish population? And what is the possibility of incidental take of young fish?
Yeah, two really good questions. The second one first, the bycatch. We did trial work in Emerald Bay. The bycatch was incredibly small. And that was without taking any special precautions. Mainly, we believe, because the depth at which the mysis live is in a narrow band that's maybe down about 40 or 50 feet. Most of the fish of concern are either lower, deeper than that, the lake trout, the mackinaw, or the kokanee are higher. So without special precautions, it was very low. We've learned now of devices that we can use to reduce that even lower. The other question was, remind me.
How will the harvesting of mysis impact the fish population?
Well, we believe it will improve them. I guess the data we have is from fishermen, and we all know that the information you get from fishermen is always correct. But we have photos that they show of in this year when the Daphnia were back in Emerald Bay, kokanee caught around Emerald Bay were huge. They weren't the usual sort of 10, 12-inch skinny little kokanee that have existed for the last 40 years, but they were fat and they had the hook beak. And because once again, they're eating Daphnia, which is incredible. It's even more nutritious than mysis are. So we think it'll improve. We also think the lake trout will improve. But if this was to go ahead, one of the things we do is be working with the fishing guides, collecting stomachs and analyzing them over time to see what the fish are eating. So this is the no regrets, the unintended consequences. We want to know how that plays out over the coming years, what the lake trout will start to eat, what the kokanee will start to eat.
Okay, and how do the small red copepods in the lake compare to Daphnia as fish food, as a fish food source?
Yeah, there are still other species, the copepods. It turns out they're much harder for fish to catch. If you've ever seen them, if you've ever been on our boat and we've shown them to you, they jump around in very erratic paths. So it takes a lot of energy for a fish to catch one of these, probably more energy than he or she gets from eating it. Daphnia, on the other hand, are like little mini buses. They just chug along at a certain pace and they're easy to catch. So yeah, the fish are obviously eating the existing zooplankton, the remaining zooplankton, but it's not nearly as nutritious for them.
Okay. Could the Daphnia decline be due to other factors other than mysis population growth? The data is convincing to support the relationship, but wondering if water temperature increase, nutrient loading, changes in mixing, stratification could be a factor as well.
Yeah, I guess it was noticed. I mean, the mysis were introduced in the mid-60s. Literally within 3 or 4 years, their numbers had just ballooned, and the data was there to show that the Daphnia, and I guess one of its relatives, the Bosmina, crashed. So the causal link is there, and it's not just at Tahoe. It's in dozens of lakes around the world where mysis have been introduced. Yeah, there are other factors that are going to cause populations of all species to vary throughout the year. It's very erratic, and the sampling is usually very sparse. As far as temperature goes, and I spent half of today talking about warmer temperatures, Daphnia actually have a very high tolerance of temperature. So the lake could warm up another 5 or 6 degrees, and the Daphnia would not be phased. Actually, they would grow faster. So in a way, they're an ideal zooplankton to be trying to bring back in the face of climate change.
Great. And then a question, I'm going to ask one more mysis question and then move to a lot of clarity questions. The question about whether this might work for Emerald Bay, but not for the rest of the lake. What is the scientific consensus, and what are your thoughts on that?
Well, there's very little difference between Emerald Bay and Lake Tahoe. It's, we've measured the primary productivity, the rate at which algae are growing there, and they're virtually identical. The nutrient concentrations between the two are virtually identical. They have a slightly different color, but that's because Emerald Bay has a larger watershed, relatively speaking, than Lake Tahoe has compared to the volumes of the two water bodies. So to say that they're different, there's no data behind that. And again, it's, without focusing on minutia, look at the big picture. Mysis were introduced to Tahoe, and the Daphnia disappeared, and it stayed that way for 50 years. Mysis disappeared from Emerald Bay, and the opposite happened for 3 years. When mysis came back, the same thing that happened at Tahoe repeated. So, I mean, these are really, really big signals. And to say, well, the CDOM in one is different than the other, I think is missing the point.
Okay, so then the last mysis question is, what would it take to move forward on harvesting the mysis shrimp, and how can people support this right now?
Right now, we're looking to do a number of things over a 2-year period. So, I mean, right now, the idea of doing this commercially is not happening. It's just we're not ready. The lake's not ready. California Department of Fish and Wildlife is not ready. What's needed is more data, and so we're looking to. Well, sorry, let me back out. What we did before is we had a very small net that was borrowed, and we learned how to troll for mysis with some success. Right now, we've been looking at working with professional net builders. We've designed a net that, based on all the data we collected, is ideal. What we want to do is confirm 2 things, is that with this larger net and higher boat speeds, we can get proportionally larger catches. And also with things like cameras and real-time depth feeds from instrumentation, that we're at a depth where the mice are. So basically, we want to optimize the process. Once we have that process optimized, it's then possible to refine the financial models and say, yep, it's a break-even proposition. It's going to cost $100,000 a year, or we're going to make money. We don't know. So we're at that point of wanting to quickly start this fall in Emerald Bay again. So right now we're at a point where the limiting factor is this new net. So there's $100,000 between doing nothing this fall and having the data to allow a larger scale experiment in Lake Tahoe next year.
Perfect. Okay, I'm going to switch to clarity topics and start with the softball again and move to the harder questions. Is clarity always measured in the same single spot, or is it measured and averaged at multiple places around the lake?
Yes or no. It's measured in two spots. But the one we always report on is the one where we take the most frequent measurements. The difference between when we compare those two spots, there's no difference in the trend. And in the past, when we've measured it at multiple places around the lake, the locations we have seem to be very representative. A lot of people want to know why we don't publish the data every time we go out. We could. It would be very confusing because the Secchi depth can change very quickly. So a single measurement may make you think that, wow, we're at 100 feet, we can relax, or it can be 35 feet and we have problems. So it's the averaging that actually gives a more meaningful value of the status of clarity.
Great. Is the amount of boating in Lake Tahoe affecting the level of clarity in the summers, and could limiting or restricting boats in the lake potentially help?
From the work we've done on looking at sediment resuspension from boats, it seems that boats don't affect the clarity at all. You may like them or love them, or like them or hate them for different reasons, but clarity should not be one of them.
Okay. What were some of the changes that led to the flattening of the Secchi depth curve? It seemed to be moving in the right direction, but what else do we think we could do to reach the goal?
Well, I just told you what we can do. No, the reason for that flattening, I believe, is a number, just the dozens, possibly hundreds of projects that have been done around the basin to stop fine particles and nutrients from entering the lake. But there's a limit to how many of these you can do. Many of the best ones, the most obvious ones, have already been done. You don't do the one with the least return first. So yeah, we could do more of those projects, but there's a law of diminishing returns there, and they're getting more expensive. Or we can take a complementary approach. So yeah, let's try to reduce to the extent possible what's coming into the lake, but once it's there, why don't we allow natural lake processes to be restored and do what they managed to do for tens of thousands of years?
Perfect. So this is along those same lines. Are there any statistics on how the new drainage around the lake on the sides of Highway 28 and 89, as well as the drainage requirements or BMPs on driveways, how that is helping reduce runoff?
Well, a lot of the motivation for doing that was based on modeling that was done 10, 20 years ago. Currently, the Tahoe Science Advisory Council has as one of its priority areas for this coming year is to look at new ways of actually monitoring the success of a lot of these projects. So as I said, many of the motivation for these projects was based on modeling, but their effectiveness has not really been monitored maybe as much as it could have been. It's a difficult thing to do, which is why it hasn't been done. But the Science Consortium is looking at new ways of doing that to see how practical it is.
Okay, what would the clarity look like if boats weren't inspected and more invasive species made their way into the lake?
Oh, clarity could be vastly improved. And I say that somewhat facetiously, but when quagga mussels were introduced to Lake Superior, the clarity improved. So this highlights this earlier point of clarity in and of itself isn't the point. The point is ecosystem health. And so, yeah, quagga mussels into Lake Tahoe would probably increase its clarity, but it would degrade the system tremendously. So yeah, kudos to the boat inspection program. It's a thankless task, probably from people waiting in line to have their boats inspected, but it's one of the more important and successful programs in the basin.
Okay, switching gears to Asian clams. Can we increase predation on Asian clams? Are there any natural predators or any uses for those clams?
We have not found them yet. And if we could, or if somebody could, then that would be a tremendous motivator to remove them, because you could at least offset part of the cost. I guess without a permit, one day we were out on a patio boat on the lake doing some of our Asian clam mat experiments, and somebody had the foresight to bring a barbecue out there, and we barbecued some, and they were tasted, tried, and maybe it was the absence of garlic and butter, but they supposedly tasted terrible. So there is not a big restaurant demand for them.
Okay. A simple question: how deep are the photos taken at for the metaphyton images?
Oh,
how deep is that metaphyton?
I don't know offhand, but it's typically 5, 6, 7 feet, something like that. It's the same depths where the Asian clams like to hang out.
Okay, and a question about the wildfires. Will the Dixie Fire and other wildfires burning this year affect the future of lake conditions?
Yeah, that's a good question, a really good question. What we know so far, we did some work a few years ago on previous fires, the Rim Fire in Yosemite and the King Fire in Desolation Wilderness, and we found there that the reduction in UV radiation changed the depth at which different zooplankton were in the lake, and so it had impacts on the food web where things are feeding. This year, we've actually been looking at the UV measurements, and there are tremendous decreases. 2 weeks ago, when we had this air quality index of 400 or something here, the UV was down about 80%. So if you have conditions like that persisting for weeks or months, there are going to be really large impacts. Some of them may be good. Actually, no, none of them are good. I mean, some of them are esoteric, changing of depth of zooplankton. Others are very tangible and real. If you have no UV in August, when the Asian clams are reproducing, you're going to have almost zero die-off of their babies. So you're going to have record reproductive success. So that's just the UV. We have another study going on funded by NSF involving ourselves and UNR and the National Park Service, looking at just what happens to the particles in the smoke when they hit the lakes. What's their fate? Do they add nutrients? Do they change clarity? Wish I could say more about that, but the data are just being collected now.
Okay, and then this is a great question. I'm not sure that this is really a TERC question, but the predicted increases in maximum daily stream flows are going to cause severe localized flooding. Is anyone assessing the potential impacts to the lake and individual structures, like the sewage pump stations, the houses, the highways, the stream banks? Are the culverts and bridges being assessed to be replaced with double or triple the typical 100-year flood sizes?
It's not a trick question. I mean, and it's a really good question. It's the same question I have. I would imagine the answer is yes. The not just the resource agencies, but the counties and Caltrans and NDOT. I mean, they're aware of these things. They build and maintain the bridges. And I guess what's new sort of with, I guess, our work and a lot of the work that's coming out is that we're starting to get solid figures where they can maybe adapt their planning standards with. So how much they've done toward this, I don't know. Are they aware of it? Absolutely, they are. And I just think, what's sort of starting to happen with, as every year goes by, is that the urgency is increasing. So it's, yeah, there are going to be a huge number of consequences. There was a study done a few years ago, I think led by the US Geological Survey, that it was a scenario testing exercise where they basically put together two very big storms back to back and looked to see what would happen to lake level and streams and landslides and all that. And it was really ugly. There was flooding of sewer stations. There was the fuel you needed to power the pumps had run out. Well, why couldn't you get any more? Well, because the road to Reno is closed and they have their own flooding. It's when these things happen at Tahoe, they're also happening in California and in Reno. And so we will be an island, self-sufficient and with our sewage pumping stations overflowing, among other things.
All right, well, let's end this on a good note. We have some dogs that are ready for mysis treats, and they are feeling okay to pay a premium for them to finance the trawler. So when will the dog treats be available, and have they been lab tested?
Ooh, no, we're not doing CAT scans, but they have been lab tested. Let me see. Well, as I said, the actual commercial production isn't happening anytime soon, but experimentation is happening. So these dog treats aren't 100% mysis. They're just a fraction of mysis and other things. And so dogs prefer different formulations. So that's one thing they're looking at. And so that's happening. There are taste panels happening from time to time up here. We can, if people are interested in getting on a mailing list to find out where these are, to get gift samples of tasty mysis treats, then go to shrimplyblue.org and you will sign up for their newsletters. And yeah, there's lots happening in that space. So hopefully we're going to get this net ordered in the next couple of weeks, money permitting, and then I think the science will follow.
Perfect. I think that's a good one to end on. So great job, Jeff. Thank you.
If anybody has any more questions, please feel free to email them to Heather.
Perfect. I'll put my email in the chat.
Thank you all. Bye-bye.